Good evening, one and all. In the last class, we had logic micro. We know that micro operations were register arithmetic, logic, and shift micro operations. We discussed the arithmetic operations and logical operation. And the last one is shift micro operations. With this, all C transfer of the data. For transfer of the data, we'll use shift transfer micro operation. That means the bits of the register are shifted. The bits of the register, you can shift the bits of the register. Right? So this shifting can be done either to the left side or to the right side. Right? So shifting can be done to the left side or to the right side. Now see how many types of shift operations we have. There are mainly three different types of shift operations. They is shift, logical shift, circular shift, and arithmetic first logical operation. So shift will transfer through registered flip-flops. Right? So it transfer. I will see the example for this. So this logical shift will transfer serial input of 0. Right? Now I already told you that shift micro operations can be done either left shift or right shift. In the same way, when it comes to this logic micro operations, the logic micro operations can also be done either to the left side or to the right side. So logic shifts. Logical shift left, which in simple words will write SHL, and logical right, which is SHR. When you write the registered when you are writing register transfer language, when you are writing this register transfer language, both the right hand side and the left hand side should have the same register. That means you are considered a single register, and the bits of those register you are shifting either to the left side or to the right side. When you can operation. So, case of logical shift, what I told you are going to shift the bits of the register one by one to the left side. The bits of the register are transferred one by one to the left side. Right? Now consider a register of type R1 which contains the data 1101. This is the original content of the register R1. Once in, let me share slides in once in. Is it visible? Is my visible? No. Is my screen visible now? Let me try it again. Now, is it visible now? Okay, I'll share the screen, ma. Meanwhile, you just listen what I'm going to share the shift remains for shift your register to shift the mic. You is mic 8 2 or then so there are mainly three types of micro. They are logical shift, circular shift, and arithmetic shift. Logical shift, circular shift, and arithmetic shift. Three types of shift micro operations. First, we'll see what is a first we'll see what is a logical shift micro operation, right? So the logical shift micro operation is going to transfer a serial input of 0. I'll tell you where the serial input 0 is transferred to the registered content. So what a serial input of 0 is transferred in this logical shift operation. Again, this logical shift can be done either left side or to the right side. First one is logical shift left, which can be represented as SHL. Logical shift right, it is SHR. When you try to write it in the form of a register transfer language, how you will write? R1 tends to SHL R1. Both the sides should have the same register name. LHS side and RHS side should have the same register name. That means you are considering the register R1 and I am applying a logical shift left on the register R1. When you see this, consider the register R2 and apply logical shift right on the register R2. Right? This is the way to represent a logical shift operation. Now consider one example. Here consider a register R1. Here I am going to explain logical shift left operation. Consider it contains the data one one zero one 1101. Now when you perform a logical shift left, which is represented with SHL on R1, what happens? The bits are transferred to the left side, right? This is LS, the least significant bit, and the higher order bit is known as MSB bit, most significant bit. As per this definition of this logical shift, what happens is the bits of the register are transferred one by one. So this LSB will come to this position, and SB data, whatever is there just before the MSB place, that will come to the MSB position after applying the shift. So the original MSB bit is discarded in case of SHL. When you see the definition, what is this? Logical shift is the one that transfers a 0 through the serial input. Now see here. So when you transfer the bits one by one to the left side, what happened? LSB bit of the register R1 comes to the first position. Then what happens? A serial input of 0 is transferred to this element to right shift, logical right shift. Right? So when you consider the R1, the data 0, 1, what happens? Bit by bit transfer. So bit by shift beyond towards the right. Right? So this maybe will come here, and this will here, and this bit will be shifted to here. Now when shifts of the to the side, here the LSB position or the LSB bit is discarded. Why? Because here got S0, this bit got LSB position. Therefore, LSB bit of the original registered content is discarded. Again, as per this logical shift, serial input transferred at the MSB position. The difference between logical shift right. In case of logical, what happens? You will be discarding the MSB position. MSB is discarded in left and LSB is discarded in right. In left, a serial input of 0 is included at LSB. In right side, a serial input of 0 is included at the MSB position. This is about logical shift micro operation. Now, come to the end of thing. Second type is circular shift micro operation. When you see the logical shift, it or right, you are going to either a MSB bit or LSB bit. If it is a left side logical shift, MSB bit is discarded. That means that data is lost. If it is logical shift right, then LSB bit is discarded or LSB data is lost. But when it comes to circular shift, the bits are going to be circulated from one end to other end either to the left side or right side, but no new information will be added and no data is lost. This is also known as a rotate shift operation. Rotate shift micro operation, because you are rotating the bits of the register from one to the another end. That is the reason we are calling it as rotate shift micro operation. So in the same way, this circular shift can also be done either to the left side or to the right side. CIL means circular shift left. CIR means shift. Just consider additional data are which contain 8 bits. Register is 8 bits. Tile 0, 1, 0. Next, when logical shift, they apply the logical shift at I'm going to explain it again. So in the previous class, we have discussed about the logic micro operation, and the last category of the micro operation is shift micro operations, right? In shift micro operation, the bits of the register are one by one. The bits of the register are shifted one by one in case of and this shifting can be done either to or to the right side. There are different types of shift migrations. One is logical shift. Last one is arithmetic shift. Logical arithmetic. Logical shift micro operation. So logical shift is the one which transfers a input of 0. I'll tell you serial by serial input. You will transfer this 0 input. So this logic can also be done using two ways. You can also perform logical shift left side or logical shift right side. When you are writing the register transfer language for the shift micro operation, how you will write? You will write like this: R1 tends to SHL, which means logical shift left. Logical shift left of R1. R2 tends to SHR of R2. That means shift right on the register R2. So in this transfer, both LHS side and RHS side should contain same register name. Right? These are the two ways of representing the logical shift. Let us see one example. Consider a register R1 which contains a data of 1101, which contains a data of 1101. If you want to perform a logical shift to left, one second. See how you will perform this logical shift to left. The bits of the register are transferred to the left side one by one. So this is your LSB bit, least significant bit, and the last bit of the register is known as most significant bit. When you are performing left, the bits are transferred to the left side like this. This one is shifted to this position. Your MSB bit is filled. So you don't MSB bit of the register R1. You can simply discard those MSB bit. So in case of logical shift left, MSB bit is discarded and you are moving to this position. So a serial input of 0 to the LSB bit position. In case of logic, the bits of the register to the left side one by one, what happens is you are going to and a serial input of 0 is transferred to the LSB bit position. Consider the logical shift right. Consider the same register R1 with the data values with the content as 1101. Now when you perform the right shift operation, what happens is the bits will be moved to the right side. 1, 1 and this 1. When you move the bits to the right side, you are going to have this LSB bit and the LSB bit is filled with this 0. You can discard this LSB position of the original data. The LSB bit can be discarded. And your MSB bit is not having anything initially. So, as per the definition of logical shift, a serial input of 0 is transferred at the MSB bit position. So, what are the 2 points to be remembered is, in case of logical shift to left, MSB is discarded. A serial input of 0 is included at the LSB position. In the same way, in case of logical shift to right, LSB is discarded and a serial input of 0 is included at the MSB position. This is about logical shift micro operation. When you see this logical shift, what happens? It can be either left or right. You are going to discard some left MSB bit is discarded, and in case of right, LSB bit is discarded. Some register data loss. Particular shift, the bits you shift the bits of the register from one end to the another end. That is the reason you will also call this as a rotate micro operation. Circular shift is also known as rotate operation. You are rotating the bits of the register from one end to another end. Here this rotate operation can also be done either to the left side or to the right side. Is circular shift left. CIR means circular shift right. Example, let us suppose you have a register with 8 bits. The range is from 0 to 7 and the content of the registers are like this: 000, 10 and 000. When you want to perform this circular shift left, how you will perform? First, simply perform the logical shift. Simply perform the logical shift. You know how to perform shift. Move the LSB side. From the LSB side, you will consider the bits and you will shift. So LSB and move the bits to the when you move the bits, what happens if it is a logical shifter? You will simply discard this MSB position and you will include a 0 at the LSB position. A serial input of 0 is included at the LSB position. But here in circular shift, what happened? In circular shift, there is no loss of data. That means the MSB bit is shifted to the LSB position. Whatever is there at MSB, you will just write the same at LSB position after applying the circular shift left. Now consider circular shift to right. Let us take the same register. When you are performing the right shift, how you will consider the data bits from the MSB side. If it is a left shift, you consider the data bits from LSB side and you will move to the left side and be copied at the LSB position. Same way, when you are performing a write shift, just consider the shifting of the bits from the MSB position and shift the bits one by one. When you shift this, what happened here? You are left with one LSB position which is not shifted. So what happens is you will shift this LSB to the MSB place. Shift, what we'll do? You will simply discard this LSB position and a serial input of 0 is transferred to the MSB position. This is logical. Next type of the shift is arithmetic shift. So the operation shift the date on a signed binary number. Arithmetic. So whatever we have discussed till now, that is logical and circular shift, they are implemented on the unsigned binary data. Unsigned binary data. But here arithmetic shift is applied on a signed binary data. That means the number can be, the binary number can be either or a negative number. You will represent the sign of the data. To a shift operation on the then you will use shift. If it is a decimal number, how you will know whether the number is positive or negative? You simply use the plus operator. But it is computer. That means everything is in the form of zeros and ones. Now, how to know whether the given number, binary number, is a positive number or a negative number? So, to know where the sign of the number, MSB bit is used. To know the sign of the number, MSB bit is used. Right? Let us suppose you have a register from which contains the data from R0 to Rn-1. The bits of the data are R0, R1, R2, so on up to Rn-1. If it is unsigned data, the total bits are used to know the, used for the original content, used as the original content of the data. But if it is a signed data, the MSB bit, you will not include this MSB bit as a content of your register. This MSB bit is used to know whether this registered data is positive or negative. So, this will contain only two values, either 0 or 1. If the MSB bit is 0, it indicates a positive number. If the MSB is 1, it indicates a negative number. Is it clear? So, arithmetic shift is mainly used to perform shift operation on a signed binary number. How to know the sign of a number? Using the MSB bit of the register value. If the MSB bit is 0, it represents a positive number. If the MSB bit is 1, negative number. Now we'll see shifting operation. Again, this arithmetic shift is can also be done as left side or right side. Arithmetic shift left and arithmetic shift right. Now, what is to be remembered in this arithmetic shift right and arithmetic shift left is, whenever you perform a arithmetic shift left, whatever the shifted value you got is a multiple of 2. Let us suppose R1 is having some data which equal to the corresponding decimal value is something equal to 8. Assume that R1 equal to 8. When you perform a logical shift operation on R1, then you as 8 into 2, 16 value. That means the corresponding binary number for 16 you will get. That is the meaning of this. An arithmetic shift left multiplies a signed binary number by 2. Right? And next one is arithmetic shift right. If the value, the decimal value of R1 is something like 16, then when you perform an arithmetic shift right on the data, then you will get a value of 8. How? 16 by 2, which is equal to 8. Excuse me, that is an arithmetic shift to right divides the number by 2. Now see one example. See, this is the example for arithmetic shift left. This is the content of the register. Arithmetic shift left is simply equivalent to shift left. How we'll see here. So when you perform a shift left, normal shift left, you know how to perform a normal shift left. Starting from the LSB bit. Starting from the LSB bit, you shift the bits of the data one by one to the left side. When you move to the left side, what happens? You left with an LSB position empty. Therefore, there you can include a serial input of 0 at the LSB position, which is just simply equivalent to your shift left operation. Now, when see here, this is arithmetic. We are performing an arithmetic shift left operation. On which data you can perform arithmetic shift? On signed numbers. On signed binary numbers. How to know the sign of the number? Using the MSB position. What is this MSB? Here the MSB bit is 0, means positive. It is a positive number. Now, any number or divide any number going to be changed. The sign not going. If I simply multiply an x with 2, you will get plus 2x. If you divide x with 2, you will get a positive value only. That means when you perform multiplication or division, the sign is not going to be changed. In the same way, here multiplication means arithmetic shift left, division means arithmetic shift right. So, whenever I perform an arithmetic shift left operation, here if the sign is different, what happens? Let us assume that here what happens? The original content contains a 0 at the MSB position. It indicates a positive number, position 0. So when you apply a shift left operation, in the resultant you have a 0 at, that means the result positive number. You may get a good out. If the 6th bit value in the original register, if this 6th bit is 1. Now, when you left shift, what will MSB position? Here at MSB position, you have a 0. Now, when you perform a shift operation, if you get a 1, then it indicates a negative number. Right? That means you don't think that it is giving you the wrong result. It indicates that an overflow has been occurred. What is this overflow and how this sign difference will come, that I will explain in the next unit. But as of now, you just remember that arithmetic shift left is equivalent to simple logical shift left. Whenever this sign change occurs, then it indicates an overflow. In detail about overflow we'll discuss later, ma. You may get confused. That is the reason I am not explaining what is overflow here. Right? With examples, I'll explain in further units. Right? Next, coming to arithmetic shift right. Arithmetic shift right is also similar to shift right operation. You know how to perform a shift right operation, right? So, how to perform a shift right operation? Starting from the MSB position, shift the bits of the register to the right side. Shift the bits one by one to the right side. But here, you are performing arithmetic shift right means what? You are going to divide the number by 2. When you divide a number, obviously the sign is not going to be changed. Therefore, whatever is there at the MSB position, you simply copy that MSB value in the shifted register. To the shifted register, simply copy the MSB. Right? These are the 2 points to be remembered in arithmetic shift. Right? arithmetic shift right means it is represented with ASHR. What it will do? It divides the number by 2. ASHL, that is arithmetic shift left, will multiply the number by 2. So always this sign difference comes only in arithmetic shift left. Why? Because in arithmetic shift right, no sign difference will come. Why? Because you are simply copying the MSB value. What if you have a 1 here, you will get 1 here. If you have a 0 here, you will get a 0 here. But this is not the case with arithmetic shift left. In case of arithmetic shift left, if both 7 and 6 bit are same, then you won't get any sign difference. Here also you will get 0. If you have a 1 and 1 here, then you will get a 1 here. But, one second. But if you have a 0 followed by a 1 here, then you may get a sign difference. This indicates positive. If you get a 1 here, it indicates a negative. And that sign arithmetic shift is that an overflow has been occurred. This is about arithmetic shift operation. The hardware implementation. How to implement using the hard component. Here take registers 4 bits. So you will consider 4 multiplexers of size 2 by 1. Consider 4 multiplexers of size 2 by 1. Whenever the multiplexer size is 2 by 1, how many selection lines should be there? 1 line, because 2 power 1. Whatever is there in the power, those many selection lines you should have. So for these 2 by 1 multiplexers, you need to have 2 inputs which gives 1 output and 1 single selection line. The selection line is only 1 means how many possibilities you can have, how many choices you will have. You will have only 2 choices. Yes value can be either 0 or 1. So if the value of yes is 0, this circuit will perform a shift to right operation. If the value of yes is 1, this circuit will perform a shift to left operation. Right? So each multiplexer is given with 2 inputs, 1 selection line, and it will produce 1 output. We'll see what are the inputs to be given to the multiplexer. Let us see one example. Here I am considering a register R, register A, which is having 4 bits from A0 to A3. The bits of the register are from A0 to A3. Assume that when you perform a right shift operation, how the bits will look in the shifted register. The MSB bit A0 will come here. This A1 will come here. A2 will come here. And you will discard this A3. And a serial input will be included at the LSB bit position. Similarly, when you perform a shift left operation, how it will be? You will start shifting the bits from the MSB bit position, right? So A3 will come here, A2 and A1. Sorry, this is from A1. A1 will come here, and at the LSB position, you will have a serial input. IL is serial input at left shift. IR means a right shift serial input, and this A0 will be discarded. Right? Now, see the truth table. From the first multiplexer, you are getting for second multiplexer, this is the output you are getting. From the third, this is the output you are getting, and from the last one, you are getting S3 as output. What are the inputs to be given? What are the inputs to be given? So each is to be given with the selection lines, right? Yes, 0 and 1. To get this HR as input, to get H0 as input, what are the 2 inputs to be given? See here, one second. Here, S equal to 0 means what? S equal to 0 means you are going to perform a right shift operation. When you perform a right shift operation, what are the shifted bits? The shifted bits are IR. IR is the serial input. A0, A1 and A2. Right? IR, A0, A1 and A2. These are the shifted bits. In the same way, when you perform a shift left operation, what are the bits? A1, A2, A3 and a serial input, right? So, when you perform a right shift operation, that is an S as IR, A0, A1, 0, A1 and A2. Similarly, in S equal to 1, which performing a left shift operation, you perform a left shift operation, bits 1, A2, A3 and IR. Now we'll see what are the inputs to be given. Multiplexer H0. To get H0, what are the two inputs to be provided? You need to provide IR, which is your A1. IR, it is connected at 0th input line. IR is connected at A is connected at where? It is connected at the first input line. So A1 connected. Here it is highlighted. This line is highlighted. A1 is connected first input line of the multiplexer. In the same way, H1, to get from where you are getting H1 as the output, second you are getting as the output. Two inputs to be connected. This multiplexer to the 0th you connect A0. So to the 0th input you should connect A0, and to the first input line you should connect A2. To the first input line, what is to be connected? A2. Next, from where you are getting this output H2? You are getting from the third multiplexer. Two inputs to A1 and A3. So, one is A1 and at the first line, what is to be connected? A3. To be of the last multiplexer. From this, you are getting H3 as your output. So, it should be given with a selection line. And what are the two inputs? To the 0th line you should give A2, and to the first line you should connect a serial input. And what should be the value of the serial input IR and IL? If in the type of this shift operation you are performing. Left micro operation, what happens? The value of both IR and IL should be equivalent to 0, right? If it is a modular shift, this IR to the MSB bit and IL will be equivalent to your LSB bit of the corresponding. The same way, you know what should be the value of IR and S of shift. But in case of arithmetic shift to right, value MSB. If it is arithmetic shift to left, then IL value to the is simply equivalent to your logical shift left operation. We'll call this circuit as a 4-bit combinational circuit shifter, right? So this circuit is showing you how to perform a logic as well as an arithmetic. All the three can be implemented using this circuit. And the last topic is arithmetic logic shift unit. Till now we have discussed arithmetic micro operations, logic micro operations, and shift micro operations. The hardware circuit to implement all the arithmetic micro operations, hardware circuit to implement all the logical, and we have already seen, just now we have seen circuit to implement all the shift micro operations. So instead of having a separate circuit for implementing different micro operations, you will use a combined circuit which is called as arithmetic logic shift. So you implement all arithmetic micro operation, logic micro operation and shift micro operation. It will take some time. So I'll continue this in the next class. With this topic of your first unit will be finished itself. I'll start the third part of your first unit, that is instruction format and so on. That may take some 6 to 7 classes with that completed. Any doubts in today's session? Please let me know if you have any doubts. If you don't have any doubts, then we'll start the quiz. Please let me know if you are having any doubts, ma'am. No doubts? Shall we start the quiz then? I'll send these slides to you, ma. Once go through these slides. If you still did not understand, I'll try to repeat this in the next class. Okay, I'm If you understand one logical shift, then you will understand all the remaining mark. You will understand circular shift as well as arithmetic shift. Repeat those again. The logical shift, should I repeat again? Let me know fast. Okay, ma, I'll conduct the quiz in the next class. I'll again explain what we have discussed. I'll just brief what we have discussed today. Okay, listen, ma. Everyone, please listen. Again, I'll revise. So, shift micro operations are mainly used for shifting of the shifted bits. You will use shift micro operation. This shifting can be done either to the left side or to the right side. There are 3 types of shift micro operations: logic, circular shift and arithmetic. If you understand this logical shift, you will understand the next 2 shifts, circular and arithmetic. All are similar only some minor changes will be there. So in case of logical shift, again this shifting can be done either to the left side or to the right side. Logical shift left, logical shift, how you will write the transfer language, register transfer language? R1 tends to SHL of R1. That means consider the register R1, apply a logical shift left on R1. Apply a logical shift on R1. Right? Now see this example, how to perform logical shift. So consider a register and 1 1 1 0 1. When you are performing the logical shift operation, consider the bits from the LSB side. This is your LSB position. This is your MSB position. Least significant bit. How you will transfer? How you will shift the bit by one? You will bit will come here, and what MSB bit is left, simply discard that bit. The bit left blank, right? So as per the definition of shift micro operation, a serial input of 0 is transferred. So include 0 and include the discard the MSB bit. Remaining bits you can shift to the left side. Logical. So here the shifting should start from this position. One by one you shift the bits. When you shift the bits one by one, you are left with this LSB position which cannot be shifted to anywhere. So simply discard this LSB and you are left with this MSB position as a blank. So according to the definition of this logic to my transfer a serial input of 0 at this MSB position. In this way, you can implement logical shift left as well as logical shift right. But what happens is, in logical shift, what happens? Either MSB bit is discarded or LSB bit is discarded. That means some data you are losing. Some data of the register is lost. So now coming to circular shift. In this circular shift, you will shift the bits in a circular manner. In a circular manner, you will shift the bit. Therefore, no new information will be added and no information is lost. Nothing is added, nothing is lost in case of circular shift. So it is also known as a rotate micro operation. Let us see how to perform this. Consider a register which is of size 0 to 8 bits and the range is from 0 to 7 bits. These are the bits of the register. When you want to perform a circular shift to left, simply you just perform it like a logical shift left. When you perform a logical shift left, how you will move the bits of the data? Starting from this LSB, move the bits to the left side. Move the bits to the left side. But the only difference is, in case of logical shift, you will discard this MSB bit and a serial input of 0 is included at the LSB position. But in case of circular shift, what happens is MSB is copied at the LSB such that no data is lost. Whatever is there here, you are just copying the same data in the shifted register. Now data will be lost and you are not adding any new data. In the same way, circular shift to right. So circular shift to right is also similar to logical shift. You know how to perform the logical shift. Starting from this MSB position, move the bits one by one to the right side. But only difference is, in case of logical, you will simply discard this LSB position and you will include a serial input of 0 at this MSB. But here in case of circular shift to right, you will copy the LSB value at the MSB position. And the last one is arithmetic shift. In case of arithmetic shift, what we are doing is the shifting operations, shift micro operation is on a signed binary number. Arithmetic shift is used to perform a shift operation on a signed binary number. What is a signed binary number? To know the sign of the number, you will use the signed binary number. Both logical and circular micro operations are performed on unsigned data, but to perform shift micro operation on a signed data, you must use arithmetic shift micro operation. How to know the sign of the data? MSB know the sign of the data. MSB bit is used to know the sign of the data. If the MSB bit is 0, it indicates a positive value. If the MSB bit is 1, it indicates a negative value. If the last bit is 0, it is a positive value. If it is 1, it is a negative value. Right? That MSB bit will be used. Now we'll see arithmetic shift left. Arithmetic shift left. It is simply equivalent to your logical shift left. So, starting from this LSB position, move the bits one by one to the left side. Move the bits to the left side one by one and discard this MSB bit, and a serial input of 0 is transferred at the LSB position. This is arithmetic shift left. Next, arithmetic shift right. Here, arithmetic shift right is also similar to logical shift right. Starting from MSB position, shift the bits to the right side one by one and discard this LSB bit. The only difference here it is, if it is a logical shift micro operation, you will copy a 0. Serial input of 0 is copied. But here in case of arithmetic shift right, is the same MSB value is copied here. The same MSB value is copied here. If you have a 0 here, you will get a 0. If you have a 1 here, you will get a 1 here. Now, see this. I already told you that the arithmetic shift is used on the signed binary data. So always the MSB bit is used for this sign. So just to know what is the corresponding decimal value of this register, you should not include the 7th bit. You should not include the 7th bit. 2 power 0 into 1 you need to include the bits from 0 to 6. How you know how to calculate this decimal value, right? 2 power 0 into 1, 2 power 1 into 1, 2 square into 2 square into 1, 2 cube into 0, 2 power 4 into 1. Like this, you should consider the bits up to 6th position only. Why? Because this is not your data value. This is your sign value. Here, the 0 indicates what? This value is a positive number. Whatever the decimal value you will get, it is a positive. In decimal, you will use plus symbol. But here in binary, you will use 0 for plus. But here what happens is, when you perform an arithmetic shift left operation, when you are performing, what happened? At this sign position, you are copying the data value which is present at the 6th bit. Right? In this case, you have a 0 at 6th bit place. So you are getting the same 0 at the MSB position in the shifted register. That means what? What is the sign of this data? This is again a positive. Right? But if you have a 1 here, then what happens? You will get a 1 here. Whenever you perform a arithmetic shift left, whatever the data you got is a multiple of 2. Assume that the corresponding binary value for this it is something like 6. The corresponding binary is 6. When you perform a shift operation, you will get this as multiple of 2. That is, this value should be equivalent to 6 into 2, that is 12. Whenever you multiply any value, the sign won't be changed. The sign won't be changed. But here, at 6th place, if you have a 1, you will get a 1 here at MSB position, which indicates it is a negative value. That means it may be equivalent to minus 12. That will come whenever there is an overflow in the data. What is this overflow? When this sign difference will come? All these things we will discuss in the next unit. So as of now, you don't require that. So what is to be remembered is, arithmetic shift left will multiply the number by 2. Arithmetic shift left will multiply the number by 2. Whenever there comes a sign difference, that means here if you have a 0 and if you get a 1 here, then that indicates that an overflow has been occurred. But that won't happen in arithmetic shift to right. Why? Because in arithmetic shift to right, we are just simply copying the MSB bit. If you have a 1 here, you will get 1. If you have a 0, you will get a 0. That means this is a negative number, this is also a negative number. You are getting the same. If you have a positive number, you will get the same positive number. And one more thing is, the arithmetic shift to right will divide the number by 2. That means if the corresponding binary value for this it is some 20, assume that the corresponding binary value for this register data is 20. When you perform an arithmetic shift right, you will get 20 by 2. This value should be equivalent to 10. Arithmetic shift right will multiply the number by 2. Arithmetic shift right will divide the number by 2. So we'll stop here. If you want, I'll again expand the next arithmetic logic shift unit, these two next class. Did you all understand? I'll send the slide just to go through those slides once. Is it clear? Did you understand or not? I'm going to end my session for today. Let me know if you have any doubts in the CAS group. I'll try to clarify those doubts in the next class. చుట్టూ మమ్మీ ఎవరి చుట్టూ